I will demonstrate the exploit of SLmail 5.5 running on Windows XP Service Pack 3. The exploit is through port 110, which is POP 3. The first thing that must be done is to fuzz the application to see if a vulnerability does exist. I am going to test this by sending 5,000 A's. I have the simple fuzzer script open to show the buffer command that will insert the A's into the slmail.exe, which is attached to the Ollie debugger on the Windows XP machine. I ran the simple fuzzer script and I can see where the EIP is overwritten with all my A's, which tells me I have control over it. However, I don't know what 4 bytes in the 5,000 that I sent took control over the EIP. Plus, they're all A's. So the next thing I need to do is to hone in and find the exact 4 memory bytes that were overwritten. And this is going to be done with the pattern offset command. But first I'm going to create 5,000 unique characters using the pattern create command, and the goal will be to overwrite the EIP with something unique other than all my A's. The first script I'm going to run is the pattern create. I'm going to create 5,000 unique characters, which I'm then going to copy and paste into my simple fuzzer script. I copied and pasted all 5,000 unique characters into my simple fuzzer script. I created a new buffer, which I will now rerun the script, and it should overwrite the EIP with unique characters. I can see that the EIP has been overwritten with unique characters, and I can also see the ASCII characters in the ESP. The EIP has been overwritten with 39794638. However, I need to read them in Little Endian order. Endianness is determined by the target CPU's architecture, and Intel-compatible processors use Little Endian byte ordering, so I need to read them as 38467939. This is a hex representation. I will need the ASCII representation to continue on with the exploit. I used a hex to ASCII translator to translate the EIP to read 8FY9. Using this 4-digit ASCII representation of the EIP, I run the pattern offset script, which will tell me exactly where in the 5,000 characters the 8FY9 falls. The value returned is 4646, so this tells me the 8FY9 starts at 4647 and goes through 4650. These are the exact 4 bytes that overwrite the EIP. I am now going to test this theory to prove that I can overwrite the EIP with the exact characters that I want to overwrite it with. To do this, I reset the buffer as follows. I am going to send 4,646 A's. Then at 4647, the start of the EIP, I am going to insert 4 K's. Then fill the rest of the buffer with 500 C's. I am only inserting 4 K's into the whole buffer, so if they land squarely in the EIP, then I am certain I have complete control. We can see the EIP has been overwritten with the K's that I sent it. I went ahead and right-clicked on the ESP and did a follow and dump. This allows me to view the characters that I sent it from the buffer, and here we see the 4 K's that are overwriting the EIP. We notice our filler C's. It doesn't appear that they have mangled any memory addresses, so there should be room for us to play with if needed. In order to determine how much memory I have in my buffer for my payload, I need to do another follow and dump on my ESP. This is going to take me to this memory address that I need to make note of. I need to write it down, then I need to follow the buffer all the way down to the very end where the last full line is. I need to write this number down. Then I need to subtract the lower number from the higher number, and this should tell me how much room I have in my buffer. Convert it to decimal, and it looks like I have 416 bytes. Most payloads are under 500, so this shouldn't be difficult. Okay, I know I have control over the EIP and plenty of room for my shellcode. I need to determine how I am going to get the application to execute that shellcode. Instead of a pop-up return, which I did in the last exercise, I am going to perform a jump ESP. I need to go into the Windows system and find a hard-coded instruction that jumps to the EIP. Then I am going to insert that instruction into the EIP, which will then jump up into the ESP where my payload will reside. I need to find a common system file that is loaded often, such as NTDLL or Shell32DLL. The reason we are using a common system file is that this payload will be portable across all Windows systems that run that DLL, and in this case it will be a Windows XP Service Pack 3 machine. To find the executables in OllyDebug, you select the E and they show up, and we are going to sort by name, and I'm going to use the user32 DLL. After selecting the file I am going to use, I need to locate it in memory. I am going to double click on the file, and then I need to do a search for command. I'm going to be searching for the jump ESP. I find it here at memory address 7E429353. However, I need to remember to read this address in Little Endian order, which would be 5393427E. This is very important so it can be ported across the Intel architecture. I have gone in and I have modified the script again. This time I have added the variable jump ESP. As you can see, it contains the memory address for the jump ESP instruction for the user32.dll, and it is inserted in Little Endian order. I have also modified the buffer. This will insert 4,646 A's, jump to the new address, and then add a whole bunch of NOPs. We are proving that we are really jumping the ESP by modifying the ESP address. This should crash the program. I ran the script again, and as you can see, it did crash. I did a follow and dump on the ESP, and you can see all the NOPs that I had added from the buffer. This is where my payload is going to reside. I need to find a payload that will work with my exploit. I can run the MFS payload-L, which shows all the payloads Metasploit supports. I only have 416 bytes to work with. I can run the name of the payload with the capital O flag to get the information on the payload. This should return information on this payload. The main thing I am looking at right now is the size. The size of this payload is 422 bytes, just a tad too big for what I'm looking for. I just need to keep looking. Let's say I decided to use a payload found in Metasploit. I would need to get the shellcode for it. The MSF payload command with the capital C option will spit the shellcode out for me. However, I need to make sure if there are required options that need to be set in the payload, that these are set in the MSF payload command, as you can see here in the localhost option. I could just copy and paste this shellcode into my simple fuzzer script. However, the odds are it won't work, and this is because of bad characters. Bad characters need to be removed from the shellcode or excluded when running the shellcode. Bad characters are one of the greatest frustrations when trying to get an exploit to work. Bad characters are application specific, and I am dealing with the POP3 server, so I need to know what the bad characters are for it. I can use MSF encode to encode and remove bad characters from my payload. I can list the encoding schemes with MSF encode-L, and I need to pay attention to the encoders being used as they are coded for different architectures. I am going to use Shikata Ganai. I need to generate the payload before I encode it. I am going to bundle the shellcode into Karen's payload using the MSF payload command. Using the Shikata Ganai encoder, I am now going to run the MSF encode command against my bundled payload and request it to remove all the bad characters of X00. It is going to generate shellcode that is encoded minus the bad characters. This shellcode is now ready to copy and paste into my simple fuzzer script. To show my exploit will work, I have modified my simple fuzzer script by adding a simple shellcode that will start the calc.exe process on the remote system. And as you can see here, it is not running. I have also modified my buffer to add the shellcode. I am now going to run my simple fuzzer script, and we should see the calc.exe process load onto the remote system. I'm now going to run my script, and as we can see, the calc.exe process is now loaded, so we're successful.